you. Thanks for sticking around for the third talk. So, right, so this is kind of a direct continuation of the colloquium, but you also will see where the results from lecture 2 get used. And so the first thing that I just want to, basically, I want to start out by recalling theorem A and talking about the structure of the proof in this theorem. So this was on the modularity of rational elliptic curves. So it was due to Wiles, Taylor-Wiles, and Roy-Conrad Diamond-Taylor. Maybe I abbreviate. So E is a rational elliptic curve. Then E is modular, i.e., there exists a modular form. And in fact, so this is a cusp form of weight 2 and some level, which is of the form gamma naught n for some integer n, actually matches the conductor of the elliptic curve, such that the associated Galois representations are isomorphic. Okay. And so the structure of the proof for this theorem is as follows. There's 4 steps. The first step, well, I mean, you can put them in, you can change the order a little bit, but you need a modularity theorem, first of all, in kind of generic cases. And you can break that up into a modularity lifting theorem and a result on residual modularity. And so there's modularity lifting, which is basically you assume so this Galois representation, let's say it's on the p-adic tape module of the elliptic curve. And this one is also the p-adic Galois representation attached to a modular form. And so you assume that the residual Galois representation, so rather than the characteristic 0 one, just the one on the p torsion, assume that this, which is a representation of the absolute Galois group of Q, into GL2 FP, you assume this is modular, which means that you assume that this agrees with the reduction mod P of the Galois representation attached to some other cusp form, call it G, which is going to be also, you assume that it's weight 2 and some level of the form gamma 0 n. So you assume this is modular. And you assume that it has large image. And so, I mean, in practice, for instance, you could assume that it's absolutely irreducible, but in fact, you can weaken this a little bit. And then you can prove, right, so the goal of modularity lifting is to assume residual modularity and prove modularity in characteristic 0. Oh, I didn't realize there were 3 boards here. And then deduce that rho E P from GQ into GL2ZP is modular. And this uses the so-called Taylor-Wiles patching method. Okay. There's another step that is the residual modularity. Right, so it's not just, okay, so we're assuming here that the mod P representation is modular. How are we actually going to prove this in practice? This actually uses, I guess, basically solvable cases of the Langlands correspondence. More precisely, uses the Langlands tunnel theorem. So in this case of rational elliptic curves, one uses the Langlands tunnel theorem to show that a particular residual representation associated to the elliptic curve, namely the one on the 3 torsion of the elliptic curve, is modular. And this uses the fact that its image is in GL2F3, and this is solvable. And moreover, it even embeds into characteristic 0 into GL2C. And so the idea is that the Langlands tunnel theorem looks at something solvable, a solvable finite subgroup of GL2C, and Galois representations valued in this, and proves that they are modular in the sense that they come from weight 1 forms. Weight 1, say. Right, so that's one subtlety. So there's the residual modularity step, but there is here a subtlety. Langlands tunnel implies that this is modular, but coming from a weight 1 form. And by the way, I've had a couple of people ask me about this example that I gave yesterday about x cubed minus x minus 1. This is something that corresponds to a cusp form of weight 1. So it's another instance of this Artin conjecture, right? So what the Langlands tunnel theorem does is it proves the Artin conjecture in the solvable case. Okay. And so the subtlety is that in order to make step 1 work, you have to produce a form of weight 2. And this only gives you a form of weight 1. And so there's an extra argument that it involves a congruence. So to go from weight 1 to weight 2, there's a congruence mod 3, basically. One needs to multiply your form by an Eisenstein series that is congruent to 1 mod 3. And since we're just interested in the reduction mod 3 of the associated representation, if I multiply by an Eisenstein series and I reduce mod 3, I still get this associated Galois representation. And I guess there's a subtlety about lifting eigenforms and producing congruences. But in any case, the idea is that you think of this form as a class in the coherent homology of the modular curve, and you use this Eisenstein series to raise your weight from 1 to 2.
There's a different E now too.
There's a different E, yes. I don't know, E3? It's not going to appear more than just here. So that's okay. Okay, and now now the idea is to combine steps 1 and 2 and get as much as possible. And so from combining steps 1 and 2, if the representation on the 3 torsion has large image, then, well, you know it's modular by step 2, and then you have the modularity lifting by step 1, and so you get the modularity of the elliptic curve. So already, if the representation on the 3 torsion is large, you get that elliptic curve is modular. So step 3 is to do a switch in order to get modularity in more cases. So this is the 3-5 modularity switch.
Can I ask something?
Yeah.
Yesterday you had FP bar, I think, coefficient.
Yes.
Does it matter?
Well, I mean, generally, when you think about these Galois representations, you can go to the, increase your coefficient field so that it's algebraically closed. But in this case, the representation is really on the 3 torsion of the elliptic curve. So it is actually valued in GL2 FP. But that's special to the fact that we're looking at these elliptic curves. And the other thing is that it's going to matter a little bit because there's a difference between being reducible when you're valued in GL2FP and reducible when you're valued in GL2FP bar. And this is going to come up a bit later. So you can have something irreducible on GL2FP, but that breaks up when you extend your scalars. Okay, but so what? We have a modularity switch. So the problem is that you can't always guarantee that the representation on the 3 torsion is large. And so if rho bar E3 doesn't have large image, then what you do is you find a different elliptic curve such that rho bar E5 is isomorphic to rho bar E prime 5. So you connect them through their 5 torsion and such that rho bar E prime 3 has large image. And then by steps 1 and 2, well, you know that this is modular. And so by modularity lifting, you know, yeah, okay, by step 2, you know this is modular. By modularity lifting, which applies because of this condition, you know that E prime is modular. And then you know that the representation on the 5 torsion is also modular. And in particular, the representation on the 5 torsion, on the 5-adic tape module is modular, and also the 1 mod 5 is modular. And then you get the residual modularity here. And so by doing this modularity switch, you can also cover those elliptic curves for which the image of the Galois representation on the 5 torsion is large, because you will know this is modular. And if the image is large, then you can lift the characteristic 0. And the way that this step is done is that basically these E primes which satisfy this condition are points, rational points on the twisted modular curve of full level 5. So kind of this condition on here fixes what the Galois representation on the 5 torsion is. And that's kind of like giving a full level structure at 5. This curve has genus 0, and it already has a rational point because that's what our elliptic curve E is. And so this is P1. And then this condition that this has large image kind of cuts out a big enough subset. Basically, the small image condition is a thin subset. And that means there are lots of rational points that you can find outside the condition of small image. And so you use the Hilbert irreducibility theorem to produce the desired E prime. To guarantee large image. Okay, so that's a modularity switch. And then if you put steps 1, 2, and 3 together, then we have gotten modularity for all elliptic curves for which either the 3 torsion, the Galois representation on the 3 torsion is large, or the Galois representation on the 5 torsion is large, or both. And so it turns out that there are only finitely many exceptions. And so that's step 4. And the reason for that is because basically you have to impose a condition, a small condition at 3 and at 5. And what you end up with, so for example, if both rho bar E3 and rho bar E5 are reducible. So with the, the representational over S3 and respectively over S5, without extending coefficients, if they are reducible, then E corresponds to a rational point on the modular curve. So basically you have a line in the 3 torsion that's Galois stable and a line in the 5 torsion that's Galois stable. And so this is a rational point on x naught of 15. So the modular curve for the congruent subgroup gamma naught 15. And this is the thing that showed up in the colloquium yesterday. So it's an elliptic curve. And I mentioned that it has rank 0 over Q. So it only has finitely many rational points. In fact, it has 8. And 4 of them end up being cusps. And you can understand the other 4 sort of by hand and show that they are modular. This uses the so-called Faulting-Serre method. So this is an elliptic curve with Mordell-Weil rank 0. Okay, and you understand the rational points by hand. Okay, so that's theorem A. And what I want to do next is go over theorem B and tell you what needs to be changed to make the argument apply there, and then go over theorem C and do the same thing. So for theorem B, maybe I don't recall it because you know what it is. And if that's okay, I'll just say it in words. So theorem B is about the real quadratic case. So theorem B, and we're looking here at F over Q, real quadratic. And E over F is an elliptic. Okay, and this one was due to Freitas, Lehong, and Zigzag. So step 1 is that there are improvements in modularity lifting that are needed in order to work more generally. So in 1, I will just say that the modularity lifting theorem proved using techniques introduced by Kisin. And one important thing here is that when you do Taylor-Wiles patching, you have to think about sort of really constructing some modules over the local deformation rings at P. So if you have a, say, residual modularity mod P, and you want to lift it to some p-adic modularity result, then the local deformation rings at P and their geometry play a key role in whether you can prove a modularity lifting technique, theorem easily or not. And in fact, this, I think before me, there were lectures, Ruth Mufang lectures by Ariane Mazard, and essentially, right, the geometry of these local deformation rings at P is really governed by this Breuil-Mazard conjecture, and somehow, yeah, like how far they are from being irreducible and understanding their components is really key in whether you can prove a modularity lifting theorem. So this connects to the lectures by Ariane Mazard. Okay, step 2 actually works the same way. So you again have this problem that you get, say, a Hilbert modular form of parallel weight 1, and you need to produce a congruence to something of parallel weight 2. And again, this is done using Hasse invariance in coherent cohomology. So step 2 is very similar. And step 3, so in this case, it's not enough to do a 3-5 modularity switch. I don't know, is there someone in the audience who can tell me why that is? So it kind of connects to what I explained in the colloquium yesterday, right? So we have something of Mordell-Weil rank 0 here, right? X naught 15. Like that parameterizes exceptions that are not going to be covered through these modularity lifting techniques, residual modularity combined with modularity lifting. But, you know, over 50% of real quadratic fields, or about 50% of them, this is going to get higher rank. And so there's going to have infinitely many points. And so it's going to be hard to prove that all those infinite families are modular. And so, right, so that's the issue. And for that reason, they do a 3-5 and also a 3-7 modularity switch, so that now the exceptions will have to have special conditions at 3, at 5, and at 7. So 3-5 and 3-7 modularity switch. And so that's one place where this paper of Freitas, Lehung, and Sixek is quite interesting. So the twisted modular curve with full level 7 is no longer just a P1. In fact, it's a twist of the Klein-Portic. So it's a real quadratic twist of the Klein-Portic curve. So it's genus 3 and degree 4, not hyperelliptic. So x cubed y plus y cubed z plus z cubed x equals 0. So this is an equation for this Klein-Portic, and you really have to look at a real quadratic twist of this and somehow use Hilbert irreducibility for this. And this is actually a more sophisticated argument. What they do is they don't quite produce real quadratic points, but they produce points that are valued in an extension of the original field that has degree at most 4. And so it's a more sophisticated application of Hilbert irreducibility, and they produce these points of degree at most 4. But the nice thing is that extensions of degree at most 4 are solvable. So again, they're able to kind of descend the modularity result to the original real quadratic field. And so this is really significantly more subtle than the 3-5 switch. Okay, and then step 4 is also that handling, let's see how I can fit all of it on the same board. Handling the exceptional cases is also more involved. And the reason for that is, so now the exceptions have particular conditions at 3, at 5, and at 7. And so the modular curves one looks at are more complicated, and they have higher genera. And so they have to develop various computational tools for understanding all the real quadratic points on these modular curves with conditions at 3, 5, and 7. Okay, so I'm now gonna, I guess, erase the board. If there are any questions about this, you're welcome to ask. And then I'll talk about the imaginary quadratic case.
I have a question.
Yeah.
Naturally, you explained that when you move from 5 to 7, things become more complicated. Wouldn't it be more natural to move down to 2? What is the reason that 2 is avoided?
Yeah, I guess, okay.
Yeah, I know 2 is always bad, but
Yeah, the problem is, I guess, that kind of GL2, F2 is just too small. So it doesn't work well. The modularity lifting theorems, mod 2, are very difficult.
Take 4, right?
Sorry?
Then take 4. It's known that 4 is sometimes the smallest you find, right?
4.
3, 4, 5, right?
I don't know how to make 4 work, but I mean, this is a good question about 2. So 2 is going to come up again, actually. Yeah, 2 is going to come up in this story when we talk about imaginary quadratic fields, but somehow it works in some ways. It helps you, but it can't. Yeah, help all the way. At least we weren't able to really use the prime 2 for what we were doing, but I'll explain how it comes up.
Maybe if one would try to go from real quadratic fields to larger totally real fields, like which would be the steps that one could hope?
Oh, and I should have said this. Thank you. So there are, I guess quartic totally real fields are known. That theorem is also known in that case. Maybe it's due to Joshua Box. And there's various other results for small degree totally real fields. And then for general totally real fields, at the moment, I think maybe we know 100% because steps 1, 2, and 3 are okay. Or maybe, yeah. But, and in general, what one knows is that everything is potentially modular. So if there was a way to go from potentially modular to modular, then you would really know it overall totally real fields.
And for all totally real fields, it would be enough to do 3, 5, and 3, 7. Modularity switch, or you would have to do something more.
So I think that the modularity lifting is definitely okay. And I mean, it's definitely, this question is definitely answered in the paper of Freitas, Lehung, and 6x. And my memory is that they do steps 1, 2, and 3, but they don't have a general method for understanding all possible exceptions. So this is my memory. That's the obstruction. But I mean, it's possible that I'm misremembering. Okay, so theorem C. So now F is an imaginary quadratic field. And E over F is a non-CM elliptic curve. And so I don't want to kind of state the theorem again. Or maybe I have to state a more precise theorem, actually. Let's see. A non-CM elliptic curve, and you assume one of the following. This is the result that we can prove. One is that the action of GS on E5 is irreducible. And 2 is that the action of GS on E3 is irreducible, and the image of GS in the automorphism of the 3 torsion is not the normalizer of a split Cartan subgroup. Then E is modular. So that's kind of, slightly different version of theorem C than what I stated yesterday. But I mean, it's really telling you what are the exceptions. And so the exceptions are when neither one of 1 and 2 holds, And here by irreducible, I really mean irreducible over F5 rather than over F5 bar. So it doesn't have to be necessarily absolutely irreducible, just irreducible. And so if neither 1 nor 2 holds, then E has to be a point on one of 2 curves. So there's x naught 15, and then there's another modular curve that has level gamma naught 5, but then has some kind of more exotic level at 3 that corresponds to this normalizer of a split Cartan. But this is an elliptic curve that is actually isogenous to x naught 15. And so those 2 curves control all the exceptions in the imaginary quadratic case. And so as a corollary, by understanding in the case where these exceptions have finitely many points, you can understand them. And then you get the statement of theorem C from yesterday. Okay, and I want to mention some previous results in the imaginary quadratic case. So there's potential modularity is known. In fact, potential modularity is even known over CM fields. You only need FCM. And this is proved in two independent ways by Boxer, Caligari, G, and Filoni. So it's a special case of what they're doing for abelian surfaces, because I guess you can view an elliptic curve over an imaginary quadratic field as an abelian surface over Q. And it's a special case of their potential modularity for abelian surfaces.
Sorry, can you say again what was potential modularity?
So potential modularity means that up to going to some extension of your original field F, so you replace F with some finite extension of it, and then you know modularity over the finite extension. And if that finite extension were solvable, you'd be in good shape. But in general, you cannot control how big this extension is and how complicated its Galois group is. And so that's why potential modularity is still some way away from actual modularity.
If it's solvable, potential modularity applies with this extension that we.
Yes, it's just that the way that the method works is it uses a result of Moret-Bailly for finding points on general, say, algebraic varieties under some local conditions. And it's very hard to guarantee that the points will be over a solvable extension. So this is not known how to, in any level of generality, how to produce solvable points. Okay, and then there's also the 10 author paper. So Alan, Caligari, myself, G, Helm, Lehong, Newton, Schulte, Taylor, and Thorne. But I will say that actually for potential modularity, the results of BCGP are a little bit stronger because in fact, they even work with arbitrary quadratic extensions of a totally real field. Just quadratic. Doesn't have to be a totally imaginary extension. Okay. And then actually, there was also a result on the modularity of a positive proportion of elliptic curves over general CM fields. And so using the really elliptic curves, this was done in this paper of Allen, Carr, and Thorne that I mentioned yesterday. And using kind of the method of Boxer, Caligari, G. Piloni, there was a student of Thorne, Dmitry Whitmore, who proved actual modularity of a positive proportion. Think of abelian surfaces. Anyway. Okay, so what are the differences? So step one is that the modularity lifting theorem is proved using the so-called Caligari-Verity method. And this is where really my work with James helped us get sort of improve the result from a positive proportion, say to 100% or all in certain cases, is that we were able to kind of prove a stronger modularity lifting theorem because we were able to prove a local global compatibility result in greater generality than in this 10-author paper. Then for steps 2 and 3, so there are residual modularity results. Mod 3 and mod 5. And these are proved in this paper of Allen, Carr, and Thorne. And for this, they actually introduce a new method because you cannot produce congruences. So you cannot use the Langland's tunnel theorem and produce congruences in the same way. So this is in the case where you have this locally symmetric space that doesn't have an algebraic structure. And we don't even see, we don't know how to see the automorphic representations of parallel weight 1 in the cohomology of this space. And so it's not clear how to produce congruences. And so this avoids Langland's tunnel and instead use a 2-3 switch to get started. So that's where the prime 2 comes in. But the issue is that somehow at 2, they have to kind of, I mean, it's a very involved and ingenious argument. And part of it is they have to put some extra conditions. And in some sense, the representation at 2 should somehow come from a totally real field. So it's not quite, what they do here is not quite optimal in the CM case. And so that's why it's not so easy to use it to improve on this result in theorem C. So it's useful to get started, but it's sort of in some way limited.
Excuse me?
Yeah.
When you say CM, do you mean the field or the curve?
So the curve is always non-CM because the CM curves are understood. So their Galois representations are abelian, and we can use class field theory. So it's always the field. Okay, and I guess I can tell you about exceptional cases. And right, so the issue is that, so ultimately, you really only have a general residual modularity result, mod 3 and mod 5. And so the exceptions are on modular curves with kind of exotic level structures at 3 and at 5. So exceptional cases lie on 6 modular curves. And these are again understood with computational techniques. So we kind of borrow a lot from the analysis of Freitas, Leung, and Zigzag. But we do have some that don't show up in the real quadratic case. And that has to do with the fact that, I know, in the imaginary quadratic case, you lose the condition that the Galois representation has to be odd because you no longer have complex conjugation in the Galois group. And so you end up seeing some extra points and somehow some non-split Cartan subgroups as the image of your Galois representation. And in that case, you actually get some, you still get some infinite families. So some of these still have infinitely many imaginary quadratic points, but there's some miracle that allows us to still understand them. So somehow half of those end up having complex multiplication and half of those end up being so-called Q curves that are well understood. So there's some miracle that really allows us to handle infinitely many cases here, but we still don't know how to handle, yeah, basically this x naught 15 and the kind of x with the Borel. So kind of gamma naught at 5 and also split Cartan at 3. This would be like x b5, b3. And so these are the two exceptions that we can't understand, but we do understand still some infinite families of exceptions. Okay, any questions at this point? If not, I want to spend the rest of the talk going into details on step 1. And really telling you about this local global compatibility result. And I guess one reason why I want to tell you about it is that we finished our paper in January of last year, and we proved kind of a pretty general local global compatibility result at L equals P. And then at the end, maybe November or December of last year, there was a very interesting paper of Matsumoto that uses this local global compatibility result to also prove new cases of the Ramanujan conjecture. And so it's been useful for modularity, but it's been useful for other things as well. Okay, so now the goal is to give you details on step 1 and specifically local global compatibility. So somehow to prove a modularity lifting theorem, especially using, the techniques developed by Kisin, you need to know that when you do Taylor-Wiles patching, that you lie on the right deformation ring at P, right? That's why the geometry of this local deformation ring comes in, but you need to know that you actually live on the right one. And that's where the local global compatibility at L equals P comes in. It tells you that you do actually lie on the right deformation ring. So more details on step 1, and particularly on local global compatibility at L equals P. And as I said, this is actually a more general result. So I'm going to now work with some finite extension of QP as my coefficients with a ring of integers O and uniformizer pi and residue field F. Okay, so these are just coefficients. And then I'm going to work with F as CM field. And with G, restriction of scalars from F to Q of GLN. So, ultimately, we're going to apply this in the case of GL2, but it also works for GLN. And I'm going to consider the corresponding locally symmetric space XK for some sufficiently small level K. Right, so this could be one of, F could be imaginary quadratic, and N could be 2, and this could be one of these Bianchi manifolds. So quotients of hyperbolic free space, but they could also be higher dimensional. Okay, and then somehow the idea is that you want to consider the cohomology of this with integral coefficients. And in fact, you want to also consider kind of some non-trivial local systems as your coefficients. And so I'm going to take lambda to be a highest weight for G. And this determines some algebraic representation, sigma lambda of G. And I'm assuming that it's defined over my field of coefficients. If not, I can enlarge it. And inside here, I can take a lattice that is maybe stable under the level of P. And all of this then produces a local system of O modules on the locally symmetric space xk. And so, this could just be O, because I could take lambda to just be trivial. But it could also be twisted, and for the proof, it's actually important to consider twisted coefficients. And then what we're interested in understanding is the cohomology of this locally symmetric space with coefficients in xk and, cohomology of xk with coefficients in this local system. And I want to look at the Heck algebra that acts on this. So again, I have some spherical Heck algebra, and I want to take so this is an abstract spherical Heck algebra that acts on this cohomology, and I want to take the maximal quotient of it that acts faithfully here. That's going to be T of K lambda. So it knows about the level and it knows about the weight. And now, so the same thing happens where you consider a maximal ideal inside of it. So a system of Hecke eigenvalues. And you have a Galois representation, first a residual one. So this was constructed by Schulze. So this is a representation of GF, and this time it's n-dimensional. I guess it's valued in whatever my residue field is, which I'm assuming is big enough. So continuous, semi-simple, and again, characterized by this condition that the Satake parameters of M match the Frobenius eigenvalues of the representation rho m bar at unramified places. Okay, so that's one thing. And if this is absolutely irreducible, then Schulze also constructs kind of a deformation of it. So somehow there's a residual one, and then there's a deformation that kind of interpolates the Galois representations attached to all systems of eigenvalues, all sort of everything that lifts this system of eigenvalues M. So there is a rho M from GS into GLN of this Heck algebra, and now I'm completing it at M. And oh, technically it's modulo some nilpotent ideal that really we can ignore. Okay, so what I want to do now is formulate what local global compatibility means. So let's see. We have a residual Galois representation, and we have a lift of it to this big Heck algebra that acts on this cohomology. And so the existence of this lift gives you a map from the global deformation ring of the residual representation, maybe with some reasonable restrictions, so like unramified outside finitely many primes, to the Heck algebra. Okay. And then there's also a restriction map from the global deformation ring, well, from a local deformation ring to a global one. The restriction of representations induces a map in this direction. Let's say I take V a prime of S. So if I have this rho M and I restrict the decomposition group at V, and maybe, okay, maybe it's not irreducible, so there's a framing. I also have to choose a basis. But after I do that, I get an induced map like this. And then basically, the local global compatibility conjecture tells you that if what you start with, for instance, has level prime to P, so has spherical level at P, for example, and has trivial weight, then I would want to be able to see this by restricting this representation to the decomposition group at V, and I should see it from the properties of the representation. And somehow the best way to formulate this condition integrally is to look at, there's a quotient of this deformation ring, which has the crystalline condition and some weight lambda. So maybe I want to assume, I'll put it here, that Kp is a product of GLN OFB. I want to assume that the level at P is actually prime to P. I mean, it's spherical, whatever, the maximal compact subgroup. And then you should be able to see this from the properties of the Galois representation. And so this is induced by rho m. And then induced by restriction. And the claim is that this diagram should actually factor like this. Right, these quotients are these potentially, so an instance of, these potentially semi-stable deformation rings constructed by Kisin. And they're quite subtle to construct. They're usually constructed in characteristic 0, and then just you take Zariski closure in the integral object. Right, so the conjecture, local global compatibility, the best way to formulate it is to say that this top map here factors through this crystalline deformation ring with weight lambda. And that's also sort of the thing that you need to implement something like the Taylor-Wells method, or I guess in this setting, the Caligari-Garrity method. So it's kind of also optimally phrased to be applied to modularity lifting. Okay, and so basically what James and I did is proved kind of a good enough version of this conjecture to then feed into the modularity lifting machinery and get a better modularity lifting theorem. So I don't know if I want to actually state. So I guess our paper is available, and so you could look at it. It's technical. I don't mind stating it, but it's just a kind of a technical result. But so this is what, this is kind of the most of our paper is proving a good enough version of this conjecture. And that improves on what's in the 10-author paper. Maybe I want to say what the state of the art is that my PhD student, Bence Hevesi, proved a version of this conjecture, not just in the crystalline case, but in the potentially semi-stable case. So this would be even harder to formulate because I need to introduce some extra things. So I can't just take this level at P. I might have to work with some higher level, and there's some head action. Anyway, it's harder to state. And this ring is more complicated to construct and so on. But like he proved kind of the best possible version of this conjecture at the moment. Except he doesn't fully determine the monodromy, but up to that, he got this. And his paper was posted to the archive, maybe also towards the end of last year. Okay. So maybe I want to end by just explaining what lecture 2 has to do with all of this. Right? So that will be the last thing to talk about. And this is already used in the 10-author paper, but it's again reused in all of these other results on local global compatibility. So I need to introduce some notation, but I'll do it quickly. It's just intuitive, I guess. So the point is, in this talk, I'm working with the locally symmetric space for GLN. And in the previous talk, I had a Shimura variety for a unitary group UNN, right? And then somehow that has twice the rank. And the idea is to connect this locally symmetric space to the boundary of the unitary Shimura variety. And so I'm going to come back to the unitary group. But so the bigger one, I'm always going to put a tilde. And this is the one from the previous talk. And inside of it, you have a maximal parabolic that is a semi-direct product of the G from this talk and some unipotent part. And then the Shimura variety, well, the associated kind of manifold to the Shimura variety. And so this would be SK tilde of C, maybe. This is the Shimura variety for the group G tilde with some level that corresponds to G tilde. And it has some dimension D. I keep that to be equal to D. It's actually n squared times x plus q, so times the degree. And I'm going to have some maximal ideal in the Heck algebra for G tilde that is obtained by pulling back M. I mean, at least abstract, like if you look at the abstract Heck algebras, you can pull it back using some version of the Satake transform, because this is a levy of this. And then the point is that we have a Heck equivariant diagram where I look at the middle degree. Usual cohomology, middle degree, homology of the boundary. So this is the boundary of the so-called Borel-Serre compactification, which is a compactification as a real manifold with corners. And on the other side, I'll tell you that first what happens here. So if I assume that the original M is sufficiently generic, then up to choosing a character twist and being a little bit clever, you can also assume it for the M tilde. And if M tilde is sufficiently generic, then we assume some genericity here, then, well, what would come next in the excision sequence would be cohomology with compact support in degree D+1. But that's something that we would know vanishes if we localize at M tilde. And so here we have a surjection. And then the other thing is, because the usual cohomology is just in degree D and above, this means that this thing is p torsion free. So this injects into HD x tilde, k tilde, mu lambda tilde, m tilde, 1 on 2. Okay. And so the idea is that H star of xk mu lambda can be shown to contribute here. So the locally symmetric space for GLN in any degree of cohomology can be shown to contribute to the middle degree in the cohomology of the boundary if you are clever about how you choose the k tilde and how you choose the weight lambda tilde for the group G tilde. And then you can lift this here and invert P, and you're in a setting where you have something characteristic 0. This can be understood by reducing to this essentially self-dual case or conjugate self-dual case. Right, and so we really used the vanishing theorem to get that this is surjective here, and also to get that this is torsion-free. So we used kind of both parts of the vanishing theorem. And then the rest is just sort of, well, over here is just technical, and over here you have to be clever about how you shift your degrees to make sure you always get in the middle, because the middle is the only one that you can control this tightly. All right, so I'll stop here. Thanks very much for your attention.